All right, let's continue working on continuous probability functions. The probability density function is what I left off with yesterday. And remember, it is the integral from a to b of f of x dx equals 1. All probability density functions have to equal 1. So this example, we're going to compute the probability that the random variable x with the probability density function f of x equals 356, 5x minus x squared, assumes a value between 1 and 2. Note, if it does not equal 1, I want you to solve for k. K will make it equal to 1. We'll explain in a minute. So we have 356 from integral from 1 to 2 of 5x minus x squared dx. So we have 356 of 5x squared over 2 minus x cubed over 3 from 1 to 2. Doing some math, we have 356, we input 2, 5 times 2 squared over 2 minus 2 cubed over 3 minus the integral of, the quantity of 1 times 5 times 1 squared over 2 minus 1 cubed over 3. Doing some quick math, we get 356. This one cancels. We get 10 minus 8 thirds minus the quantity of 5 halves minus 1 third. More quick math, we get 356 times 10 minus 8 thirds minus 5 halves plus 1 third, which is 31/6. Yes, I put it in my calculator. I didn't know that number. And 31/6 times the 356 that you already had is 31 over 112. Now that did not equal 1. So as is, it is not probability dense. But what can you do to make it probability density function? You can reciprocate that number and you have a k, and k is going to equal 112 over 31. So if it does not equal 1, you find the reciprocal of the answer, and that is going to be your k value. That will be very important. All right. Then we're going to go on to 3 more different types. And the first one is uniform density function. It is the simplest of the probability dense functions. F of x equals either 1 over b minus a. If a is less than or equal to x is less than or equal to b, that will actually be your integral note. Or 0 if x is less than a or x is greater than b. Note, there's your picture. It's from a to b. It's just absolutely what's in between there. That is it. So, a train leaves a terminal every 40 minutes. What is the probability that a passenger arriving at a random time to catch a train will have to wait more than 10 minutes? So the first thing you need to know is, what am I going to put in as my function? 1 over b minus a. Well, your b is 40 minutes. Your a is 0 because you must have started from 0 to 40 minutes is what you're going to wait for. So 1 over 40 is going to be your function, 1 over b minus a. Now, what is your integral going to be? It's more than 10 minutes. So more than 10 minutes is from 10 to 40. That is a 40 up there. I integrate 1/40th, and I get 1 over 40 times x. From 10 to 40. I put 40 in. I get 40 over 40 minus 10 over 40 equals 30 over 40, or 3/4. Typically, your answers are in percentages. So 75% wait more than 10 minutes. That would be your uniform density. It's the easiest one. You wish that I had like 10 of those on your assignment and your test, but I don't. The next kind is called exponential density function. Let x be continuous random variable if f of x equals, now they give me this equation formula, lambda e to the negative lambda x if x is greater than or equals 0, or 0 if x is less than 0. This lambda is a Greek term for a variable for the number of arrivals, or if it's a number, if it's just lambda, it's for the number of arrivals. If it's 1 over lambda, it's for the average waiting time. So the average arrivals is lambda, the singleton, just the number. If it's 1 over lambda, it's for the average waiting time. That's the difference on those two. And that's probably going to be the hardest part of picking out a problem when you're doing these, not anything else. All right, we're going to start this example 5. Airplanes arrive. So right now you're thinking arrive. You're going to use the arrive is going to use the lambda. At an airport follows an exponential density function with the average of lambda equals 15 arrivals per hour. Determine the possibility of arriving within 6 minutes. Well, this is 6 minutes, and that's an hour, so something's got to change. So you're not going to change your lambda. You're going to change this time. 6 minutes is going to equal 0.1 of an hour. 6 over 60. All right, so now I have to figure out my equation. My equation is going to be from 0 to 0.1 of 15 e to the negative 15x dx. That's the easiest part once you get to that point. Okay, I integrate that. Well, the 15 stays solid. E to the negative 15x over negative 15 is my integral of e to the x. Okay, the 15's cancel, but the negative does not. Make sure you keep the negative. That's going to be critical. And it's from 0 to 0.1. So now I stick in my 0.1. E to the negative 15 times 0.1 all over negative 1 minus e to the negative 15 times 0 all over negative 1 equals, quick math here, negative, because the negative on the bottom, e to the negative 1.5 plus, because I canceled those out, 1 because it was e to the 0. So I got 0.777 or 77.77% probability arrives within 6 minutes. So those are the easier ones because it arrived within 6 minutes. All right, we're going to do one more kind of that type. And then we're going to do a new type. So example 6, again, these are all from page 497 to 500, I believe it is. Yes. From past data, it is known that a machine produces one defective product every hour. Again, I'm going to put 60 minutes there because I don't know whether it's going to be in hours or minutes. To detect a defective part, an inspector walks up and tests a continuous stream of products. He uses the exponential density function, that probability of what happens if A, the inspector waits less than 30 minutes. Now again, I'm in minutes here, so I need to be in minutes there. Okay, so you've got to be in the same time before finding a defective one. So the first thing you're going to have to say is, what is my lambda? Now this time it's waiting time, and waiting time for lambda is 1 over the number, 1 over 60. So 1 over 60 is my lambda, e to the negative 160x dx, and it is less than 30 minutes, so I'm going to go from 0 to 30. I am going to integrate that, 1 over 60, e to the negative 160 times x, divided by negative 160. The 160ths cancel. Again, the negative did not cancel. From 0 to 30. You plug in your 30 into the x, e to the negative 160 times 30 over negative 1, minus e to the negative 160 times 0 over negative 1. Well, 30 over 60 is e to the negative 1/2, negative e to the negative 1/2, plus 1, because this was e to the 0, and that was 1, and a negative of negative made it plus 1. Doing some quick math in the calculator, I found out that that is 0.393469. I move the decimal place 2 places. I get 39.347% probability less than 30 minutes. Now that was letter A, so we're going to do another one here in a minute for letter B. So here we go. An inspector waits more than an hour and 15 minutes. So again, up here, this is in 60 minutes. So now this is in minutes. So an hour and 15 minutes is going to be 75 minutes to find a defective product. But it's more than 75 minutes. So that means 75 minutes to infinity. Well, infinity is very difficult to integrate. So instead of doing that, you're going to do the opposite. So let's do less than 75 minutes and then take 1 minus that, or the complement. So 1 minus the integral from 0 to 75 of 1/60th e to the negative 160x dx. I integrate similar to the one before, 160 e to the negative 160x divided by negative 160. The 160 is canceled, the negative does not. I place in my numbers 75 into there. 75 over 60 becomes 5/4, and the e to the 0 again was going to become 1. I had to do some fast math. I'm losing space on my board here. And I get 0.713495. However, remember I was doing the complement, so don't forget. So what's 1 minus 0.713495? That's 0.286505. So you move the decimal place over, and it's 28.651% probability more than 75 minutes. All right, so those are your two exponential density problems on that one. All right, now we have one more type of problem. It's called expected value. So expected value, I consider one of the easiest ones. And when you're looking in the word problem, you're looking for the word expected. If x is a continuous random variables, for the probability density function f of x, as a is less than or equal to x is less than or equal to b, then the expected value of x is e of x equals integral from a to b of x times the function f of x dx. In other words, you literally multiply your function times an extra x immediately. Expected values are average mean. Okay, so that's all the definition and the formula. So what does the problem say? A passenger arrives at a train terminal where the train arrives every 40 minutes. Determine expected waiting time using the uniform density function. Well, uniform density function was on the other page, and that was 1 over b minus a. So 1 over b minus a was 1 over 40 minus 0 times the x because it was expected. So x times 1 over 40 from the interval of 0 to 40 dx. So I integrate the x is x squared over 2. 1 over 40 times x squared over 2. Put my 40 in. 40 squared over 2 minus 1/40th. This should be parentheses. Excuse me, I didn't have the parentheses around there. Okay, and I'm going to get 40 over 2, which is 20, minus that should be 0, because that's quantity there. So my answer is 20 minutes expected wait time. So expected wait time, you multiply the function times x. So anytime you see the word expected in the word problem, you're going to multiply whatever function they give you times x. All right, I've given your assignment. It is on the syllabus, page 501 and 503, 3, 5, 11, 13, 14, 15, 17, 19, 25, 27, 29, 30, and 40. Note, I would say the hardest part is to determine which of these you're going to use. So determine which probability density formula you're going to use. Then you have to find out what the equation is going to be over what your interval of A to B is. Another super note I wrote. Tomorrow at Hangout, I'm going to teach you a new button in your calculator. So hopefully you'll all attend so you can learn the new button in your calculator. All right, that's all for 7.3. It's not going to be easy. It's mostly word problems, and you have to figure out which function or formula to use. Thank you.